afternoon session, which starts with Martin Bridgeman from Boston College, who will speak about renormalized volume.
Thank you very much. Thank you all for being here. Thank you to the organizers for the invitation. It's always great to be in Rio. Can you all hear me? Okay. So I'm going to talk about some renormalized volume. It's based on a number of projects with a number of different people in various combinations. And I thought, given that the conference title has surfaces and hyperbolic manifolds in them, that I would try and give a little bit of an overview of this sort of area. So, okay, so what am I going to, first of all, think? I'm going to just consider S some surface in M, hyperbolic tree manifold. And so I want to talk a little bit about properties or how you describe surfaces in tree manifolds. So it has an induced metric G. And it has what's called a shape operator. Which is a linear map on the tangential of the surface given by taking the covariant derivative of, this is the normal vector. So B has eigenvalues, the principal curvatures, and G and B are what you call the fundamental pair. And sometimes the standard notation is to call G the first fundamental form, and then this to be what I would call G dot B, which I'll define as where G dot B is G of B x y. So you're sort of pairing this linear map with this metric to give you another symmetric bilinear form. And then we won't be using it much, but there's a third one and a fourth one. And these three are called the three fundamental forms. Okay. So there's a classic fact that if F is immersed in M hyperbolic, then we have GB satisfy the following equations. The determinant of B is the curvature plus 1, and this is the Gauss equation. And the second equation, which is the Codazzi equation, which looks a little bit more scary, is that the exterior derivative with respect to the connection of B is 0, and this is the Codazzi. Did I get the two D's? It's one D and two Z's. Okay. Okay. So I'll just call these GC. And let me just say what does this mean? It means it's of a pair. It's just minus A of the bracket. Okay? So it just says this quantity is 0. Okay. So if you're in hyperbolic space, you satisfy these Gauss-Codazzi. Okay? And there's a classic theorem that says, a theorem of Bonnet that says if S is simply connected and G, B are a pair satisfying GC, then there exists an F from S to H3 in immersion with GB being the fundamental pair. So if this satisfies Gauss-Gadazzi on a simply connected surface, then you actually get an immersed surface. Okay, so in some ways this describes, this is sometimes called the classification of immersed surfaces. Okay, excellent. So that's a little bit on this. So I wanted to talk a little bit about how there's a duality between this sort of immersed surfaces and what's going on, how these surfaces give a dual construction on the boundary of hyperbolic space, and where you get a dual set of equations that describe the immersed surfaces, but now in terms of the structure on the boundary of hyperbolic space. Okay, so let me talk a little bit about that. So this is sort of introduced by Krasnov and Schlenker. And what we get is we think of this surface, so we have a surface, S, here, and we have a normal flow on it, where we can flow for time t. And so we get a family of surfaces propagating by doing normal flow. And we can think of these as giving us pairs GT, BT. And it turns out that these can be easily described. So what is GT? GT turns out to be just the original G changed by a linear map on the tangent space. And what is this linear map? This linear map is so when I do this, I mean that this is the pullback. So you operate this on both vectors rather than writing this long expression down twice. And there's another quantity, which is just switching these two. And BT is just AT inverse CT. So you can completely describe the sort of these surfaces and their metrics and their shape operators in terms of the original surface. Okay. Any questions? Okay. Excellent. So let me describe the duality. So the duality is, what we want to do is, we want to think of, you have surfaces, and then you do this normal flow, and what we want to think of is taking some limit of this normal flow to get something that sort of is on the boundary. So there's a natural way to do that. How do you do that? Well, you let G hat be just the limit as t goes to infinity of scaling this. And so we'll scale it by cosh squared t, because that actually gives you a finite limit. And what is this? This is just a pullback by the identity plus B. And it's natural to define the shape operator at infinity to be just identity plus B inverse times the identity minus B. And in fact, so this is my dual pair. So simply put, surfaces in hyperbolic space are described by their fundamental pair satisfying this equation. And there's a converse. And I should have said here also the fact is that F is unique up to Mobius. So the fundamental pair completely describes the surface this way. Yes?
Are you supposing that this flow has no singularity?
So yeah, it also describes when it has no singularity, because when things go wrong here, this is when it goes wrong. So for example, if this was convex, there would be no such problem. You could just flow. If the B has so you might get singularities, but in general you can just, like for example, if you're looking at convex, you can just flow. Okay, so we have this duality, which is you start with GB, a surface, and you get a G hat, a B hat. And you can go back and forth between them. G turns out to be 1/4 the identity plus B hat of G hat, and B is just the same form for this. So you can go back and forth between these two, and so you can also define I hat you can define the fundamental forms at infinity. So these are called the forms at infinity. Okay, so that's just some setup. So let me just introduce the following equations. First of all, so Krasnov and Schlenker, a lemma there says of Krasnov and Schlenker says if GB satisfy the Gauss-Cadazzi, then G hat, B hat satisfy some other equations. What are those equations? They're the trace of B hat is equal to minus twice the curvature and, well, the Cadazzi equation again. So this is sort of the dual equations to the Gauss-Cadazzi. So we'll just call these GC hat, the dual Gauss-Cadazzi equations. Okay. So it turns out that actually, what's hat? K hat is the curvature of G hat, of G hat. Okay, so G hat is a metric and a linear map on the tangent space, and so K hat is its curvature. On S. Okay, so it lives on S, and it lives on S. Okay, so what do we actually have is the following. So there's a theorem. Krasnov, Schlenker, and myself and Ken Bromberg did this in roughly around the same time. So this satisfies Gauss-Cadazzi if and only if P hat, B hat satisfies Gauss-Cadazzi hat. So this is a way of maybe transferring the problem of immersed surfaces onto the boundary. And actually, what I want to first show you is that actually what this is the Epstein surface construction. Okay, so before I do that, I want to introduce another object that's sort of not so familiar to people, called the Osgood-Stowe differential. And so this was this is work of Osgood and Stowe, obviously, as a generalization of the Schwarzian derivative. So let me just say what that is. So it actually was in a very, very general context. You had some Riemannian manifold, and you had phi, a smooth map, and you could, the Osgood-Stowe differential was a quadratic differential described as follows. It was the Hessian of phi, with respect to g, minus the differential of phi, tensor with itself. And then you take this is the traceless part. So you take this object, with respect to g, it has some trace, and you subtract off the traceless. You have some trace, and you subtract off the trace times the identity, and you get a traceless quadratic form. Okay, so what is this object? It's sort of it's a way to compare a metric and a function, but actually what it's mostly used for is comparing two metrics that are in the same conformal class, or it can be used to compare a metric to a projective structure. And basically you want to think of, you've got a metric always, and then this other function could be the thing that describes the conformal factor of the second metric with respect to the first. So I won't go into the whole theory, but let me just say you can use it to define Q or Osgood-Stowe, where this is a projective structure on S, and G is a metric in the conformal class. So you have a projective structure, and what it is has a very nice form. And I'll write it as just in local coordinates, so you can write it in local coordinates in terms of these z's and so it's because it's traceless. That means that if you wrote it in complex coordinates, it's going to have and symmetric, it's going to have this form. Okay, and what do I want to say here is z is some projective coordinate, and I can actually describe what Q is. Q is very simple. It's phi of z, z, minus phi z squared, where g is just e to the 2 phi dz squared. So if you What I'm saying is you give a projective structure and a metric in the conformal class. The metric will have this form in terms of some projective coordinate, and this is the quadratic differential. So it's mostly not going to be holomorphic. It's going to be just some quadratic differential. So why did I bring this up related to this? It turns out that this is exactly what B hat is. What B hat is coming from this Osgood-Stowe differential. So I'm going to define the following. I'm going to define a second fundamental form with respect to a projective structure and a metric. And it's going to be twice the Osgood-Stowe differential. I don't have any choice over how people normalize the Osgood-Stowe, so there's a 2 in there, minus the curvature of G times G. So that gives you some 2 form. And it's equal to G. I'm going to define its sort of associated linear map B, but just the linear map that gives you this when you compose it with G in the way I was saying. Okay. So the theorem I want to say it's me and Ken Bromberg is that G hat, B hat satisfies the Gauss-Cadazi equations, the projective Gauss-Cadazi equations, if and only if there exists sigma, a projective structure, such that its second, the second fundamental form of this is just the projective structure, this form associated with this projective structure. And not only this, this is unique. So what I'm saying is that if you have a metric and you want to satisfy the Gauss-Cadazi equations, there's a unique projective structure that gives you this. So satisfying the Gauss-Cadazi equations is the same as pairing your metric with a projective structure. Okay. And now if we just cycle back through if we want to build surfaces, if you take a metric and a projective structure, you get this form here, and it satisfies the Gauss-Cadazi equations at infinity, or the dual ones, and it has a dual that gives you a surface. Okay? So that's sort of the description of sort of the dual description of these surfaces is essentially being described by projective structures. Okay. So what I want to say is that this is sort of like Epstein's construction of surfaces, which are now called Epstein surfaces. So what's an Epstein surface? You take the boundary of hyperbolic space, and let's just say we just take a simple case where we take a domain. And on that domain, we're going to just take some rho. Some rho is a conformal metric. On omega. And Epstein, so what did he describe? He described a surface, S rho, which here's S rho, completely described by this conformal metric. How did he do it? Well, he gave a very nice geometric picture, and the geometric picture was the following. You take a point in the domain, so if you have something in the domain, you let this be the visual measure in H3. Or sorry, yeah, nice. Not the visual measure, sorry. So you take a point here, you define a horoball, which is all the points x in H3, such that the visual measure at x, evaluated at the point, is greater than or equal to the metric at this point. So what is this visual metric? The visual metric, so if I have a point which is the origin, this visual metric is just the regular metric on the sphere. And all other ones are just gotten by taking a Mobius transformation to any other point. So what you get is, you get a horoball for every point, and what is it? It's a horoball centered here, and every point gets a horoball, and this here is the envelope of all those horoballs. So it's got this beautiful geometric picture that the surface here is actually the boundary of the union of all the horoballs of every point in omega. So that's the Epstein surface. And
So what are the restrictions on omega? It's just there's no restrictions?
no restrictions. So what is, how does this relate to here? If I have rho and I have an omega sitting inside C hat, I've got a conformal metric and I've got a projective structure. So this is my G hat, sigma hat, and this gives me a G B by duality, and that's that surface. So the nice thing about this is it sort of reduces everything to doing some two-dimensional linear algebra, two-dimensional some derivatives, some complex analysis, and you get you can sort of describe these surfaces, and you don't have to deal with the envelopes, and it gives you sort of just another viewpoint of where these surfaces are sort of naturally described as sort of the duality between surfaces in hyperbolic tree space, which are given by a pair, and their dual pair, which we could either take as G hat, B hat, or the projective structure that is the unique thing that satisfies that equation. Okay, so that's, and so let me say something a little bit more. I said something about the Schwarzian derivative. If this is a domain, and we take the hyperbolic metric, like it's a simply connected domain, then this is the Schwarzian derivative. So that's the Schwarzian derivative. Okay. Any questions? Okay. So that's just a sort of setup to sort of what I want to talk about was renormalized volume, but when you start varying things with respect to renormalized volume, you're looking for the derivative of renormalized volume, and you start having to look at quadratic differentials, and these are the things that describe the variation of renormalized volume. Okay. So I promised Franco I'd actually get the definition of renormalized volume now. So, so let me look at M, a convex, co-compact, three-manifold. And so my general picture of this is that I have M is H3 mod gamma, and you have something that has some flaring ends, and it has some surfaces and infinity of different colors. They may all be genus 2 just because I'm lazy, but it's got this compact core. And when you lift it and you look at the limit set is just basically different copies corresponding to each boundary component with the different colors corresponding to lifts of the different ones. And did I have a green? Green, okay. So this picture is not quite accurate. What I've drawn here is they all look like disks. So that's the equivalent of me saying that the manifold has boundary which is incompressible. So if its boundary is incompressible, then when you lift, you just get disks. And that's sort of equivalent to having boundary incompressible. So I'm just drawing the incompressible boundary case. So for these objects, we have this, we can take a conformal metric rho on the boundary at infinity, which is just the domain of discontinuity mod gamma. So we take some conformal metric in here, and what does that give us? Well, it gives us an Epstein surface, which I may be regretting drawing different colors now, but you get an Epstein surface for each. And so, yeah, rho and the projective structure on the boundary infinity. This is a projective structure because you're quotienting by Mobius transformations. Gives Epstein surfaces. That bound some tree manifold with boundary. So this is bounding n rho now. I can rub this out. And I have this object here. And so what I can do is I can define a volume. So I can define the W volume of rho to be the volume of n rho minus 1/2 the integral of the mean curvature along the boundary. And that's the W volume. So that's the W volume. You take a conformal metric, you take the associated Epstein surface. And now let me just stop and say for once, we have an immediate description of the principal curvatures of this surface, the boundary and all this, just in terms of, we know B hat, and B is just this simple inversion. And so we completely describe the geometry of this object. And we have, we also have, we take, well, let's just take rho m to be equal to the hyperbolic metric on the boundary. So you can take the hyperbolic metric, that's a conformal metric, on each of these components, and the renormalized volume of this manifold is just the W volume of the hyperbolic metric. And as I said before, this Osgood-Stowe differential, when you take the hyperbolic metric, is the Schwarzian derivative. So all the geometry of this surface and the behavior of this is all going to be described by the Schwarzian derivative. Okay, so let me look at how I'm doing. Okay, so let me just say some properties. So it turns out to have some very nice properties. If you scale this, it just changes by a factor of the Euler characteristic. And if G1 is less than or equal to G2, and both are non-positively curved, then W of G1 is less than or equal to W of G2. So it has a monotonicity. And that for fixed area G, W is maximized at the constant negative curve metric. So the hyperbolic metric maximizes this among all metrics of the same area. Okay, so it's got some very nice behavior. What do I want to do with it? Well, you can use it to study renormalize or volume of the convex core volume of this. So when you have a convex co-compact tree manifold, its convex core is compact, and Vc of M is the volume of the core, and this is less than infinity by definition. And so what we can do is we can fix N a tree manifold and let Cc of N be the space of convex co-compact structures on the interior of N. And we have a theorem of Beers and others that if the boundary of N is incompressible, then this space is just the Teichmüller space of the boundary, where you're just sending M to its conformal structure. That. Okay? And so I'll leave that up there. So what does this tell us? That tells us that if we recall that the cotangent space of Teichmüller space at a point X is just the space of holomorphic quadratic differentials. So that means that we can define a one form, so a natural complex one form as follows. So you take your manifold and you let omega naught be a component. This is a connected component. And then you have some map uniformizing it. And so you have some uniformization map. And you take phi tilde to be just the Schwarzian derivative of this. So that gives you a quadratic differential on the disk. And this is going to descend to a quadratic differential on the boundary infinity of M. So the process is you uniformize each piece. You take the Schwarzian derivative, and you descend to quadratic differentials, and then you have a complex one form on the space. Okay, so you have the following. So you have a map from M to, so you map M to phi of M, and this is a complex one form on the space of convex co-compact structures. And with this complex one form, you can define a vector field. It's a one form because the Schwarzian derivative is a quadratic differential, right? Sorry. It's a quadratic differential. And the space of quadratic differentials is the cotangent space, right? So you have the one forms on this Teichmüller space are just the quadratic differentials. So if the Schwarzian derivative in particular gives you one. Okay, so the vector field is just, you take the dual of this. So you take the vector field at M to be just minus phi of M over the hyperbolic metric. And that's a Beltrami differential. Actually, I have this phi bar. And so what happens? You've got a vector field on the space of all these objects. What does the vector field do? So the vector field makes the boundary totally geodesic. So theorem by for n acylindrical, all flow lines limit to M geodesic. The unique structure with totally geodesic boundary. So this flow, if you're acylindrical, will turn this picture into a picture with round circles. So this means that M geodesic looks like you've got totally geodesic boundary. So I'll just draw the picture up here. It'll just look like circles. And there's only one unique structure that has that property. Some of my circles are not so good, and they all look like the same color. And the flow just finds this structure and flows down. Okay. Just checking on time. Oh, I got some time. Okay, so the flow flows down here, and I haven't described what acylindrical is. Acylindrical means you don't have any non-trivial cylinders, but I wanted to just sort of like point out why this is sort of something that crops up as an obstruction in a sort of. So what does it look like? What does it look like when you're cylindrical? So acylindrical, incompressible means these are all disks. If you're acylindrical, it means they're all disks, but it means something more. And what it means is that you can't have two regions. What would it look like to have a cylinder? And I could have two regions touch, and you have two geodesics here, and they form a cylinder that doesn't appear on the boundary. Okay? So there's a so acylindrical, I should have, well, this is already acylindrical because they're not touching at all. But you can also see here why you can't uniformize this to have totally geodesic boundary. Because you can't have two circles touch in 2 points. So circles don't touch in 2 points. So if you had two circles, the best they could do, if these did touch here and you had a structure where these are circles, that can't happen. That's why there's, when it's acylindrical, you can only expect to get such a structure. Okay. Any questions? Yeah. Okay. Excellent. So, what's that? I mean when I say totally geodesic boundary, I mean the boundary of the boundary of the convex core is totally geodesic. Thank you. Okay, so.
If it is cylindrical, is it like degenerate or something?
Yeah, so that's so what does the flow do if it's cylindrical? That's sort of work in progress, but you do have right, well, let me just say something. So you do have the following. If this is incompressible, the inf of renormalized volume is the same as the infimum of convex core volume. And it's attained if and only if n is quasi-Fuchsian or n is acylindrical. So with this is a theorem of Storm, and renormalized volume does the same thing. It has infimum, and it's only attained here. It's attained just because it's attained at 0 at the Fuchsian locus. Here it's attained uniquely there. So theorem of Storms is that if you're incompressible, the convex core volume has a unique minimum if and only if it's acylindrical or quasi-Fuchsian. Otherwise, it's not attained. In female, it's not attained. So one project is, without going into too much detail, is to explore what happens in the cylindrical case, and that gets into breaking the manifold down into its windows pieces and analyzing that. But maybe for the shortness of time, I'll go in a different direction and maybe just talk a little bit about Loewner energy in the last 5 minutes, if I have 5 minutes. Yeah, okay. I might get back to it if I have a chance. So it turns out that we can also have infinite well, let's just say the universal Weil-Petersson. Curves. So I'm going to define T1 to be a universal Teichmüller space. That's another way of thinking that is Teichmüller space without a group. So there's no group. What is that? It's quasi-circles in the plane. And so I'll draw, here's a quasi-circle. It's got a region omega and omega star inside and outside. And if F is a map from here to here, uniformizing omega, and phi is its Schwarzian derivative, gamma is called the Weil-Petersson curve if the integral of the L2 norm of this over the disk with respect to hyperbolic area is less than infinity. So that's what's defined as Weil-Petersson curves. And so they form a subset of this. And out of probability theory and complex analysis, there's something called the Loewner energy, L, which is some functional on these curves, which I'm not going to be able to describe. And this Loewner energy has the same variational formula of renormalized volume. So one of the projects was like, can you define the renormalized volume of this object? And how much does it relate to what we did in this case, in the convex co-compact case? And so this is a project with Elin Wang, and so let me put the names up there. So this is so what did we show? So first of all, we can use the same flow on T0 of 1. So you're flowing on quasi-circles that are Weil-Petersson, and that, again, the theorem is that the flow lines limit to the unit circle. So this flow is, I guess, curve straightening or something. It naturally flows any Weil-Petersson curve to a curve to the unit circle. And the question is, does renormalized VR make sense? And is VR equal to L? And so we have the following theorem, is that we have, under certain restrictions on the curve, for gamma in T naught of 1, C5 alpha, so it has to be smooth to order 5. Renormalized volume is the same as Loewner energy. And actually, I have to put in a 4 here, I think. Okay. So you can build this. Now here in this case, you've got your region is not compact, so you have to do a little more hard work. This here comes out of some kind of probabilistic theory where you define sort of some energy on the curves, and the fact that these two are the same is pretty surprising. We think it's true in general, but we haven't been able to prove that. And I think I will stop there.